Hello, SPH3U. Welcome back. Today, we're taking a look at the concepts of work, energy, and power. These are all terms that are used in everyday language, but have a very specific and somewhat nuanced meaning in physics. Let's talk about the concept of energy to start with. We use energy in everyday language all the time. You talk about, for example, the energy industry, which comprises of the oil industry, nuclear power, wind, solar. We also talk about energy in terms of our metabolism. We buy things called energy bars, which are just another way of marketing high energy foods. Again, we're using the term energy. However, we don't really actually have a really good understanding exactly what energy is. And don't feel bad, no one else does either. Our current definition of what energy is the ability to do work. That is the official definition of what energy is. Now, in terms of a quality of a definition, that ranks fairly low. That would be the equivalent of saying the definition of a car is something that takes you from point A to point B. It's true, that is something that the car does, but that hardly describes the actual nature of what a car is fundamentally. We're at that same impasse when it comes to energy. We don't actually really know what it is. We only know what it does. And we know some other things about energy. We know some of its properties. So let's talk about some of these properties first of all. First of all, energy can be transferred from one object to another when work is done. So we know that energy can move from one object to another. I like to think of energy as currency as in money, because in many ways it behaves in the same way. So we can transfer energy from one object to another. What that means is that if we're doing that, one object is losing some energy, but the other object is gaining that same amount. The actual energy itself is simply just being transferred. Now, energy comes in many forms, and these forms are interchangeable. So we have basically two categories of what we talk about energies. We have these things called kinetic energies and these things called potential energies, which we'll define in more detail. But for example, you can take fuel like gasoline and convert it into heat by burning it. And then you can take that heat and turn it into kinetic energy, whereas kinetic energy implies motion. So the vehicle actually moves. So this is actually transferring energy from one form to another and moving down the line. So energy has many forms. Energy also can be stored and used later to do work. Now, when we refer to the stored energy, that's where we get this quote unquote potential type energy, which again, as I said, we'll discuss a little bit later. Now, here's the big important one. Energy is always conserved, meaning that it cannot be created, nor can it be destroyed. The implications of this is fairly profound. This means that the total energy in the universe today is the exact same amount of energy that we had in the universe yesterday, the day before, last month, last year, 1,000 years ago, 1,000,000 years ago, 1,000,000,000 years ago, all the way back to creation, the Big Bang. So the total amount of energy in the universe has been the same amount, and it'll be the same tomorrow, 1,000 years from now, 1,000,000, 1,000,000,000, 1,000,000,000,000, so on and so forth. So the total energy in this closed universe of ours is a constant, but energy is constantly being transferred from one object to another. Now, at some point, all of this energy will eventually be converted into heat and dissipated away into the environment and then ultimately out into space in the form of low-level infrared radiation and latent heat. So eventually, and this means at some point, the universe will die what is called a heat death, if our current model is in fact correct. Eventually, the energy is going to be so spread out, so far away, that the universe will become a cold place where all that energy is just this low level amount of heat distributed over an impossibly large volume. Let me give you an analogy. Let's say, for example, you have a space heater, all right? And the power goes out in your, the furnace goes out in your home. So the furnace goes out in your home. You have this little space heater. Now, you have a decision. You can take you and that space heater and bring it to the smallest room in your house, or you can take you and that space heater and bring it to the largest room in the house. Most of you know intuitively that it's wiser to bring that space heater into a smaller room, because inside a smaller room, that amount of energy being produced, specifically heat energy produced by that space heater, is only required to heat a smaller volume, which is a lot easier to do because the energy isn't spread out. The larger the room, the more that energy is spread around, and of course, not as warm. So when the energy is focused, it's highly concentrated. When it has to occupy a larger volume, it is more diluted, for lack of a better word, meaning that it can't do as much quote unquote work when it's spread out so thinly. So now this little bit of waste heat that we're talking about, this latent heat, unfortunately, it's not able to do any usable work because it's so widely dispersed away. And so eventually we are going to run out of usable energy, but that is very, 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 very far in the distant future. So nothing that we need to worry about in our lifetimes or even in the life expectancy of our species. So let's take a look at how this energy transfers, how they occur. So let's talk about what's happening in the sun for a moment. All right. Now, the sun started off with a large amount of interstellar gas, and a bit of gravitational potential energy started causing the gas to coalesce in on itself. As the gas started being attracted to itself, and we talked a little bit about that Newton's universal gravitational force, all objects that have mass have gravity. The mutual gravitational pull of this gas increased as the gas became more dense. As it became more dense, it produced more gravity. As it produced more gravity, more of these other gases started to fall in. Now, when these gases start to fall in, they gain speed. Well, speed is a form of what's called kinetic energy, and we call that bulk kinetic energy. So when an object is moving at a fast rate, we call that bulk kinetic energy because the whole thing is moving. Heat is associated with the vibration of the atoms within the molecule itself. So as the atoms internally vibrate, that's what we describe as heat. And when the actual entire chunk of stuff moves from point A to B, we call that bulk kinetic energy. So these gases start falling in, they start colliding with each other, causing huge vibrations, which causes a huge heat buildup. And eventually, when there was enough gas, enough pressure, and enough heat being generated, then another form of energy was released called nuclear energy. Now, we're going to talk about nuclear energy in a moment because that is related to this right here. But anyway, let's continue on. So nuclear energy then takes everyday matter and turns it into energy. And then, of course, things get even hotter. So we get even more kinetic energy being generated in the forms of heat and bulk. And then that heat and bulk, that heat energy and bulk kinetic energy gets high enough that it turns into a form of radiant energy. Radiant energy, and you can see the root word here is radii, as in radius, radiation, radio, radial. These are all things that are basically moving along the radius of a large sphere. So the sun is burning quite brightly. It's actually nuclear fusion. It's not technically burning. And the radiation moves away from the sun in the forms of infrared, visible light, radio waves, ultraviolet, X-rays, and gamma rays. Most of the energy that makes it to our planet is in the form of infrared radiation, visible light, and ultraviolet, which is very important for plants and also what gives us suntans during the summer. Now, this radiant energy then gets transferred into another form, and it gets formed into chemical energy through an act of photosynthesis. So the plants absorb this energy and produce chemical energy in the terms of carbohydrates. And this process also gives off heat, and that heat gets dissipated out into the atmosphere. So this is actually an important process. The Earth has to have an ability to cool off naturally. That's why global warming is such an issue, because we are actually affecting this natural process where the excess heat from the sun is dissipated out into space. And it's important that we have that balance because we don't want the Earth too cold and we definitely don't want it too hot. So then this chemical energy is in the form of food, and then herbivores eat that food. and then carnivores and omnivores then eat those herbivores, and the cycle then continues. This implies here, this whole chain here is very important. Our entire existence is reliant on this chain. If this did not exist, no life or meaningful amounts of life could exist on Earth without the power of the sun. We're literally consuming sunlight. There are some species that exist in the depths of our ocean where there is no solar radiation that's able to get down there because of the depth of the ocean, but they survive another way by converting directly chemical energy into carbohydrates, and we call that chemiosynthesis. And they get that chemical energy as a result of volcanism. Things called smokers, which are these superheated volcanic gases and liquids that come spewing out at the bottom of the ocean, high in sulfur content, and there are bacteria that actually can feed on that and support small ecosystems, but ecosystems nonetheless that don't rely on the sun, which is pretty cool. All right, so let's actually focus on this part, the nuclear energy. Because I did say that energy can't be created or destroyed, but it comes in many forms. And not just many forms of energy, but it actually comes in the fact that energy and mass turn out to be one in the same. So matter and energy are completely interchangeable. And most people have seen this formula at some point. E is equal to mc squared. E stands for the amount of energy, and that is in a unit called joules. Mass is in kilograms, and C represents the speed of light, which is 3 times 10 to the 8 meters per second squared. This is a remarkable amount of energy in everyday matter. And to give you a little bit of context, most of you are familiar with the only 2 instances in which nuclear weapons were used against a civilian population. And that was during the time of, during World War II, when the cities of Hiroshima and Nagasaki were bombed. The amount of energy released in the bomb that destroyed Hiroshima was enough to destroy the center of the city, level most buildings, and kill a huge number of the citizens. It was a terrifying example of nuclear energy being used in the most horriblest of ways. But the amount of mass that was converted into energy during that event was only 12 grams. 12 grams is a tiny amount. That is basically like a small candy. This implies that everyday matter contains an extraordinary amount of energy within it. And if we were to convert ordinary matter into energy, it would be an absolute remarkable amount of energy stored within. The issue is, of course, we don't know how to do that. And, you don't want to be converting matter to energy on the regular. So let's continue on. So when we talk about energy, there are basically 2 categories. And again, remember, we don't really know what energy is. We know what energy does. So there are 2 types. There are the potential energies, and then there are the kinetic energies. So potential energy is defined as stored energy, and it's as a result of that object state, which means that the energy isn't being used yet, but it is stored for later use, which makes sense why it's called potential energy, because it has the potential to do work. The more common types of potential energy, chemical potential energy. So chemical potential energy, for example, gasoline, a candle, food. These are all examples of energies that are stored within the molecules of a substance and then later can be used for work. Now, we consume food that is stored in our refrigerators and our pantries. Then, of course, when we consume it, we digest it, and then the body converts it into ATP, which is the power molecule that runs our bodies. Now, excess food gets stored in the body in the form of fat, and fat is another type of potential energy that can be later used during a food shortage. So if, for example, you're a bear and you're getting ready for the long winter, you are packing in as much food as possible, gaining as much fat as possible. That way you can survive the winter without starving to death. Next, nuclear. So nuclear energy is stored in the nucleus of an atom. And tremendous amounts of energy are released when these atoms are split or fused. The sun uses a process called nuclear fusion, where hydrogen is fused together to produce helium, where on Earth, we are only able to achieve nuclear fission, which means fission means to break apart or to essentially cut in half. So there are uranium isotopes that are relatively unstable, and when bombarded with neutron radiation, they break apart, and whenever they break apart, they produce more energy than the energy is required to break it apart. And then you can, in a controlled way, run a nuclear power plant and generate electricity this way. Or in a rapid succession, as what happened during the bombing of Hiroshima and Nagasaki. Interesting to note, the largest nuclear device ever detonated on Earth, not against the civilian population, thankfully, but during a test was in 1960. It was developed by the Soviet Union. It was called the Tsar Bomba. And the Tsar Bomba was the largest nuclear device ever released, and it eclipsed the size of the Hiroshima bomb by dramatic proportion. And to give you a little bit of context, the bomb was detonated 10 kilometers above the surface in Siberia, and the shock wave was intense enough that it was able to break windows as far as Norway. The light from it was able to be seen as far away as England, and the shock wave produced by it circumvented the Earth 7 times before it was no longer detectable. If that bomb was to be released above London, Ontario, at that height, everything between London and Guelph would be incinerated. That's how big of a bomb that was. So there is tremendous amounts of energy associated with the atom, terrifying amounts. Next, gravitational. Gravitational energy is the stored energy of an object due to its position above a large celestial body. So, for example, if you lift a rock and you drop it onto the ground, that is a form of gravitational potential energy, then later used and converted into kinetic energy. So, this is all based on how high an object is and how massive it is. Elastic potential. This is the energy associated with the stretching, bending, or compressing of elastic type material. So a slingshot, for example, or a spring. These are all examples of elastic potential energy. And as when you're a little kid, they used to, you sometimes go to like a fast food joint like McDonald's, and they would have like little toy wind-up cars. Inside those cars were either springs or elastics, and then you would twist them up, and then when you released, the car would move forward. So that's another form of energy, potential energy. And then electric potential energy. Electric potential energy, this is associated with things like capacitors, batteries, these sort of things. So these are things that store energy later for use. And then magnetic potential energy, and this is energy stored within magnetic fields. It's very similar to a spring type potential energy, except using magnets in order to be able to do that. Now, kinetic energy. Kinetic energy is the energy of motion. So the types of kinetic energy are associated with anything that moves. So bulk kinetic energy. So this is the energy associated with the entire motion of an object. So like a rolling cue ball, or a car that is driving, or a boulder that's rolling down a mountain. Sound. Sound is the energy transmitted molecule to molecule with a medium in the form of a longitudinal sound wave. So there has to be, to be kinetic, there has to be travel involved. So sound can move from point A to point B. Sound requires a medium. For us, that medium is air. Sound also travels in the water. That's how whales communicate. So that is a form of radiation, another type of radiation form. Thermokinetic energy. This is the energy associated with the random motion of molecules within a substance. And again, the hotter an object is, the faster the atoms vibrate. Next, radiant energy. And again, this is associated with energy of electromagnetic waves, such as radio, light, X-rays, infrared, visible light. These are all examples of radiant energy, including the dangerous type, the ultraviolet. Well, X-rays is a dangerous type. Gamma rays, which are the most dangerous. And then electric energy. So this is the energy associated with moving electric charges, electric current. And this is why your power supply for your computer, after heavy usage, starts to get warm. Okay, so let's start getting into some concepts here. Specifically, we're going to talk about the concept of work. Now, the word work in physics means something very different than it does in everyday use. So, for example, the work is defined as a force through a displacement. Now, the concept of work is what we call a scalar. Work is not a vector, but it's actually the product of two vectors, right? So work is equal to the force vector times the displacement vector. Now, this is something that you won't know yet in grade 11, but you'll learn something about this in grade 12. And this is something called a dot product. And what this means is that for work to occur, the force and the displacement have to be in the same line. So the easiest way to think about this is work is done is if the object gets more energy. So let's do a little example here. All right, so now let's say we have, so here's our ground, all right? And I'm going to draw a little box, all right? So this box has mass. So right now, if this box is just sitting here on the ground, right? If this box is just sitting here on the ground, it doesn't have any potential to do any damage, right? Or anything at all. It's not going to move. It's going to sit. Now, let's say we lift it, okay? Now, we lift this box to some height, okay? So this is some height above, and the box has some mass. All right. Now, if we were to let go of this box, clearly it would drop and smash onto the ground. Now, if this box was, say, something like a heavy weight, the higher we raise it, the harder it hits the ground, right? The lower it is, the less damage it would do, or less violent the impact would be. So by lifting this box, we have done work. Well, how does that apply to the definition? Well, in order for us to lift it, we have to apply a lift force, a force lift. And this box has moved through a vertical displacement. The box has moved in this direction here. So the force and the displacement are in the same line. So this object has gained more energy. Well, what happens if we lower the box? Okay, if we lower the box, we're taking energy away from it. So in this case, when the box got lowered, it actually lost energy because we were still lifting. Our force was still up. But in this case, our displacement was negative. So a positive force and a negative displacement gives us a negative result. In this case, we have done negative work. Okay, so what does negative work mean? Negative work simply means that we have taken energy out of the box. So the box, we gave it a form of energy called gravitational potential energy. When we lowered it back down to the ground, we took that gravitational potential energy away. Now, that energy has to go somewhere. It's not actually lost. That gravitational energy went into us. We absorbed it, and we absorbed it in the form of heat. And that heat eventually goes off into the environment. So the energy is lost into the environment. So we have done negative work on the box, but something else gained that energy. All right, so now let's give an example when work is not done. So let's say we're lifting this box. So these. All right, so we've lifted the box. So we start from the ground and we lift the box up like this. So we have done work because we have increased its height. That is our displacement. It went up like this. All right, so now the box has a certain amount of energy. So let's say we're just holding it at this position here. Now we're still lifting it, but what happens if we shift it over to the right here? So now when we did that, our displacement was in this direction. Well, here, if you look, the displacement and the force are at 90 degrees to each other, all right? The box didn't get any higher. So by moving laterally here, no work actually was done on the box. That doesn't mean we ourselves didn't do work. All I'm saying is that the work that you and I did to move this box laterally didn't go to the box. Where'd it go? Just got wasted into the environment as heat. So yeah, you're exerting this effort. You might even be breaking a sweat. Well, that's sweat that you're breaking is because for your body to be able to do this job, your muscles have to fire up. When your muscles have to fire up, there's all sorts of motion. The blood is pumping through your body. The molecules are sending ATP to your muscles to keep them active. So there's all sorts of kinetic energies happening inside of you, but that energy isn't going to the box. So we are using calories. We're burning calories to do this, but the actual box itself doesn't gain it. It's just getting wasted out into the environment. So in that case, work is not being done on the box. Again, you are using energy, but it just isn't being delivered to here. Because no matter how long you hold this box, it's not going to hit the ground any harder the longer that you hold it. What matters is how high this box is, and what also matters is how heavy the box is. Those are the two factors that are going to affect the impact of this box if we were to drop it. All right, so that's where this formula comes in. So now I mentioned that work is equal to force times the displacement. Well, that equation here only works is if they are parallel to each other. Well, what happens if the forces aren't parallel? Well, then we use this equation here. That is the magnitude of the force times the magnitude of the displacement times the angle between them. So if we look in this example over here, the displacement and the force, right? And let's just move that over like this. If you look at the angle between them, well, that's 90 degrees. Cos of 90 degrees is 0. As a result, no work is done. So that would go to 0. There would be no work in that case. All right, so that's the first formula that we're dealing with work. So in this case here, so let's take a look in this first scenario. All right, so in this first scenario, if we're pushing an object and we're moving in the same direction, work is being done. So if you apply a force, and let's say this thing has wheels, by pushing it in this direction with a net force, the object is going to accelerate. If the object is accelerating, that means it's increasing speed. If it's increasing speed, that means it has the energy of motion, which means that it has kinetic energy. So we're taking our energy in our body in the form of ATP and converting it into kinetic energy, the energy of motion. Whereas in this example over here, if we hold the box, if we're holding the box and we move it from this position to this position here, and then we come back to a stop again, the key is we have to come to a stop. So during the time when we were moving, yeah, there was a little bit of kinetic energy, but once we stopped, that extra kinetic energy is gone. Where'd it go? In the environment is heat. And if we're just holding it here, the ability to, the energy associated with the gravity is 0. Has not increased, not 0. There's a 0 increase in gravity, so no work is done. So again, there has to be a change in energy associated. So either the object has to increase in speed, or it has to increase in height, or it has to get hotter. These are all examples of work being done on something. There has to be a change in the energy in the object. All right, so let's take a look at these two examples here. So we have a 5 kilogram sled, and it's being pushed with a net force of 15. Just something very, very simple. Okay, so a net force of 15. We have 5 kilograms. How much work is done on the sled if the sled moves 5 meters? So if we're applying 15 newtons, 5 meters, we get 75 newton meters or 75 joules. We don't use newton meters, we use joules as our form of energy. Now, if we go 10 meters, well, that gives us 150 joules. We have double the amount of energy. Well, what form would that be in? If there is no friction. Of course, there's friction in real life, but if there is no friction, then that simply means that the longer or the further that we apply that force, the faster it's going to go. So in this case, we have 150 joules of kinetic energy versus 75 joules of kinetic energy. The object will be moving faster in the scenario here. Okay, so what happens if work, to calculate work when F isn't constant? Now, the formula that I gave you earlier here was that work is equal to F times D, right? Now, assuming that they're parallel. If we were to graph this, this with a constant force. So if we take a look, and next thing I'm going to do, so that is our force, and down here would be our displacement. So let's say we moved it from one position to another. So that's a position of 0 and some unknown position over here. The formula, force times distance, if you look, that's just the area. Area is equal to length times width, or in this case, force times our distance. So if we calculate the area underneath this plot, that will give us the amount of work. Well, that applies no matter what the shape is. So here we have force times displacement, and here the force is increasing linearly as the distance goes. All right, so in something like that, we just calculate the area, which would be, 1/2 base times height. Easy peasy, lemon squeezy. So let's take a look at this example here. Find the work done on a 500 gram car with a spring-loaded motor over the first 7 meters. All right, so with a spring-loaded motor, as the car moves along, the spring unwinds and becomes weaker. So at the very beginning, the spring is producing 75 newtons. Once we reach the 10-meter mark, the spring is completely unwound and it's producing 0 newtons of force. So that's also 0 newtons. All right. So the question is, we want to figure out how much work was done during the first 7 meters. So if we look at the first 7 meters, we can break this up into 2 shapes, a rectangle and a triangle. And if you're really on the ball, you could also recognize that this is a trapezoid, right? But we're just going to do rectangle and triangle. So the area of the rectangle is base times height. So that part gives us 70 joules. Of the triangle, the base is 7. The height is 25 minus 10. So that gives us 52.5 Newton meters or 52.5 joules. So in combination, the work is going to be 70 plus 52.5, which is 122.5 joules. What form is that energy going to be in? Well, assuming no friction, which of course is inaccurate to do, but if we were to assume no friction, that would be in the form of bulk kinetic energy. In other words, the car would continue to accelerate and get faster and faster and faster until it reached the end here when there was no force left on it. And if there were no friction, the car would just continue to go at that max speed that it was after the spring unwound forever and ever. Amen. But in real life, we have the force of friction, and the force of friction slows things down. And eventually the energy gets converted into heat, sound, and vibration. And then the final resting point would be just plain old heat. All right. So that's all there is to that. Okay. So now we did mention earlier, I talked about gravity, gravitational potential energy. So how do we figure out gravitational potential energy? We have a formula for it. Well, and here's how we're going to look at this formula. When we lift an object, at the very minimum, our upward force has to be equal to our weight, right? So the upward force is counterbalanced with the weight. So if we're lifting something at the minimum condition, we want to lift it at a constant speed. And to do that, the upward force and the force of gravity are equal but opposite to each other. So the magnitude of F upward is equal to the magnitude of the weight of the object. Next, so when we lift our object here, we are moving at a constant speed, all right? So for some of you who are sort of wondering how this is actually possible, let me just give you an example of what would happen in real life. So let's say that is our lift, and down here, that is our force of gravity. Okay, well, actually, let's be consistent, F upward. All right, now, just to get it going, we obviously have to, for a brief second, our upward force has to be larger than our gravity, but then it goes back to normal again, all right? And when we do that, we then slowly move up at a constant speed, all right? Then we get to this position here, all right? And when we get to the top, what happens is this is our lift force that was, let's bring these guys over here. In order for it to stop, the lift force has to be slightly less than the force of gravity until it stops, and then we balance that out again. So at the beginning, you give it a little oomph at the beginning to get it going, and at the end, we relax a little bit to get it to stop. But on average, what this means is the upward force is on average equal to the weight or the force of gravity. So 1, 1, 2, and this is 2 over here, and 3, and this is 3 over here. Okay, so, and that is just the explanation we were going on about there. I don't know why it's just these dots. I'll see if I can correct that a little bit later. All right, so now, just erase that for now. Okay, so let's take a look at what's going on with this thing. So we know, and I'm just going to do the diagram to the side here, just to explain it. It's the same thing as the diagram over there, but it's always easier just to see it developed in real time. So here we have our object. All right, now, we're just going to focus on, I'm just going to call it FL for force lift. So when we lift an object, we're applying this lift force and we're lifting it through some height. All right. So now we lifted this object through this delta H. All right. Now we know that work is equal to force times a distance. All right. Or times displacement technically. Let's just work with the scalars because they're parallel. So in this case, that's our FL times our D. But our FL is actually the same as the force of gravity if we're lifting at a constant speed, which is equal to mg. So we can replace FL with mg. So that's mg times d, all right? But the d that we're talking about, that's displacement, that's just this. So the d that we have here we can replace that with our delta H. So work is equal to mg delta H. This is actually one of our first equations. So this is the work associated with gravity, and it's only dependent upon the mass of the object, the strength of little g, and the change in height, delta H. Well, let's continue with that. So that's one form of the equation. Next, but this mg delta H business is the same as H2 minus H1, which is equal to, using distributive property, mgh2 minus mgh1. Let's move the ground out of the way. Sorry, mgh2 minus mgh1. So when we look at these individual terms, this mgh2 and this mgh1, this term here, we refer to that as the gravitational potential energy at position 2. So gravitational potential energy, E gravitational position 2. That's what those things mean. This would be the gravitational potential energy, or energy associated with gravity, at position 1. So our work is also defined as the change in gravitational potential energy, where Eg is equal to mgh. So this is our gravitational potential energy equation. So let's do a little easy sample problem with this. Now, we should clarify a few things first of all, make sure that we all understand what the units are. The m is in kilograms. That's the mass of the object. The g on Earth is 9.8 meters per second squared. The important part is it's never negative. It's just the magnitude. So when we use the symbol g, it's the magnitude of the acceleration due to gravity. And h is our height in meters. All right. So I can't stress this enough. Whenever you see the letter G, do not ever put negative 9.8. It's just 9.8, just the magnitude. All right. So let's do an example. A 100 kilogram mass is raised from 10 meters to 30 meters. All right. So work is equal to mg delta H. So the mass in this case is 100 kilograms. Little g is 9.8, and our delta H is our final position, which is our H2 minus our initial position, which is our H1. So that gives us 100 times 9.8 times 20. So that's 19,600 joules of energy. To give you some context, a 100 watt light bulb, traditional light bulb, not the new LED ones, but the old school ones. And if you've ever touched one of those old school light bulbs, you know that that's not a wise decision. They get super, super hot. And a 100 watt light bulb is pretty bright. The amount of energy required to lift this would be enough to run that 100 watt light bulb for 3 minutes and 27 seconds. My apologies. Try that again. 3.27 minutes, right? Yes, because it's not time isn't metric. So that would be 16 seconds. My apologies. All right. So now, let's do another example here. So what happens if let's take a 50 kilogram mass and lower it from a height of 25 meters to 10 meters. Well, that's our mass. That's our initial height, and that is our final height. So that would be our H1. This would be our H2. That would be our mass. So our work is equal to mg delta H, which is mg H2 minus H1, adding an extra step here just to see how it's done. And we're left with 50 times 9.8, 10 minus 25. And that gives us negative 7,350 joules. That means energy was taken away from the system. So that implies that we've removed gravitational potential energy. That energy has to go somewhere. So if you and I are taking this object and lowering it, that energy is being absorbed into our bodies in the form of heat. That's why these jobs tend to make you a little bit sweaty. Because not only you're absorbing the energy, but your body actually has to fire up its muscles in order to be able to do this. If we were to actually just drop this, then that would turn into bulk kinetic energy as it is falling. So as it is falling, it turns into bulk kinetic energy. What happens when it hits the ground? Well, depending on the type of surface that we have, it will make a thud or a crack sound. The fact that it makes a sound means that some of that energy gets converted into sound energy. If it puts a dent in the ground, some of that energy went into permanent deformation. And then ultimately, the rest of the energy goes into heat. So this is also another reason why, if you've ever done any sort of housing work, like framing or anything like that, or worked with a hammer, if you hit a hammer often enough, the hammer actually starts to get hot. So if an object actually impacts the ground, heat is generated. If the object is big enough, moving fast enough, you can actually generate a lot of heat. Hence, when a meteor hits the surface of the Earth, if it's large enough, it produces enough energy to actually create a massive fireball. Hence the thing that took out the dinosaurs. Mass extinction events are associated with the bulk kinetic energy of an asteroid or a meteorite being converted into heat very rapidly, causing tons of damage to the biosphere. All right, so and there's a couple of more work examples there. The other concept that I want to point out here is this is the key thing. With gravitational potential energy, we don't care about the path that we take, we just care about the change in height. So whether we move straight up or we take some random path here, the amount of energy that the object gains is the same in both cases. It's all about the amount of energy. And this is why it's weird, the definition of work. Your effort doesn't mean anything with respect to the amount of work necessarily. So whether you lift it from here to here, or if you exert all this effort to move it around like this, the box receives the same amount of energy. This is actually where we talk about efficiency. So this second way is less efficient because your body is using more energy, but it's not going into the intended target, which is the box. So the amount of work that you do in situation 1 and 2 is identical. However, the amount of energy that you give off or consume in order to do the job, well, this job number 2 would require more energy from you than this one. So this method is less efficient. Now, bulk kinetic energy. So the concept of bulk kinetic energy is the energy associated with motion. And here's the formula. All right, so we've got 1/2 mv squared. The next thing is, how do we get this formula? All right, well, we're going to take a look and we're going to drive it over here. So let's get our little setup here. So here's our road, and let's say we have a box on wheels. So we're assuming that there's very little in the way of resistance. All right, and we're applying a net force. So let this vector represent our net force. So this is our F net, okay? And our object is moving through some distance here. So it eventually gets over here. Okay, so we know that work is equal to F times D. Technically, it's the vectors, but if they're in a straight line, we can just work with the magnitudes. Now, that actually really means F net times D. But we know that F net actually equals MA. So MA times D, which makes sense because we all know that work makes you mad. No? Okay. Anyway, so mass times acceleration times D. But if we start, say, at rest, we know that by applying a net force, the thing is going to accelerate. So the displacement can be given by the following kinematics formula, V1 plus V2 times delta T. So we can make a little replacement. So that is equal to MA times 1/2 bracket V1 plus V2 times delta T. Make that a little bit better. All right, now I want to clean things up a little bit here. Now, this 2 is in the denominator. This V1 plus V2 delta T, this is actually all technically part of the numerator. All right, so what I'm going to do is I'm going to bring my 1/2 out front, and I'm going to have my M, my A, and I've got my V1 plus V2 times my delta T. All right, however, acceleration is equal to delta V over delta T. All right, so what I'm going to do is I'm going to replace my acceleration with delta V over delta T. So I get 1/2 M delta V over delta T times V1 plus V2 times delta T. Well, the delta T's cancel out very conveniently. So I now have 1/2 M delta V times V1 plus V2. But delta V is the same as V2 minus V1. And V1 plus V2 is the same as V2 plus V1. Now, if you look, we have a binomial times a binomial. And depending on who you had for math last year, you either would use distributive property to do this or a method known as FOIL to expand this. But the trick is, what you should also recognize is that this, ladies and gentlemen, is actually a difference of squares. But if you don't recognize this as a difference of squares, we can do it old school. All right, so we'll use distributive property. So I'm going to take this and I'm going to distribute it across like that. So we'll use distributive property to do this. So this gives me, and I'll put in square brackets, this is going to be V2 bracket V2 minus V1 plus V1 bracket V2 minus V1, my square bracket. Now, using distributive property, I get V2 squared minus V1 V2 plus V1 V2, because V1 times V2, minus V1 squared. Well, you can see these two, they cancel out. So now I'm left with 1/2 m bracket V2 squared minus V1 squared. And that's the difference of squares. There's your difference. There are your squares. Difference of squares. Okay, so work is defined as 1/2 m V2 squared minus V1 squared. So this is our first version of our kinetic energy formula. All right, next thing I'm going to do is I'm now going to distribute this 1/2 m through the brackets. So I'm going to get work is equal to 1/2 m V2 squared minus 1/2 m V1 squared. So this right here, this refers to our final kinetic energy. This 1/2 mv2 squared, that represents our final kinetic energy. 1/2 mv1 squared, that represents our initial kinetic energy. So work is defined as the change in kinetic energy, where EK is equal to 1/2 mv squared. Our mass is in kilograms, our speed is in meters per second, and our kinetic energy, that is in joules. If you note, the more important factor is V. Speed has a much more important factor in terms of kinetic energy than the mass does. If you double the speed, you actually quadruple the amount of kinetic energy. Whereas if you double the mass, you only double the amount of kinetic energy. So speed is much more important. This is also the reason why the stopping distance is so much higher when you go faster, because you have to dissipate far more kinetic energy in order to be able to do that. So kinetic energy is more affected by an object's speed than it is by its mass. So let's take a look. Here's an example. So how much kinetic energy does a 50 kilogram mass have if it's traveling at 0 meters per second, 2 meters per second, and 4 meters per second? Well, the amount of kinetic energy when it's 0 meters per second, well, that makes perfect sense. Since you're not moving, there should be no kinetic energy. It's not going to hurt you. If it's moving at 2 meters per second, when we apply this in here, 1/2 times 50 times 2 squared, that gives us 100 joules of kinetic energy. But now let's take a look. We double the speed and we quadruple the amount of kinetic energy. So speed is more important in terms of kinetic energy than the mass. Conservation of energy. All right. So we've mentioned earlier that energy cannot be created or destroyed, but only converted from one object to another. All right. So we're going to be working with mostly gravity and kinetic energy. So we're going to use conservation of energy to solve these types of problems. So an example, an object dropped from rest from the top of a building will lose gravitational potential energy, but that loss of gravity has to turn into kinetic energy. That's why when things get dropped, they accelerate. The taller the building, the more EG is lost, resulting in a greater increase in kinetic energy. This is why when things are dropped from greater heights, you have a much larger impact velocity. So let's consider the situation where we're dropping an object from a building that is 100 meters tall. All right, so I'm going to work this out. It's already been worked out for you, but I'd like to work it out with diagrams and all that jazz. All right, so let's draw a building here. So here's our building. And let's try to draw that so that it looks actually not like some enormous highlighter. Okay, so here's our building, and that is the ground. All right, so I'm going to call this up here position A. I'm going to call this down here position B. So what we know at position A is that the initial speed is 0 meters per second. All right, now we know that the height at position A is 100 meters because that is the height of our building. Our building is 100 meters. Now, the speed at the bottom of the building when it lands is unknown. We know that at the very bottom, we reach a height of 0 meters. All right, so let's do some analysis here. So we want to determine what the speed is at the bottom of this. Well, what I know is the following thing. I know that the total energy at position B at the bottom is equal to the total energy at position A. This is conservation of energy. So the energies associated are at the bottom, we have the gravitational potential energy and we have the kinetic energy at the bottom. And then we have the gravitational position energy at position A and the kinetic energy at position A. All right, so now a couple of things. When we look at this, I know that my height at position B is 0. So that means this goes to 0. And the reason why that goes to 0 is because it's equal to mgHb. And since m times g times hb, if hb is 0, then this whole thing is 0, which makes sense because when we're on the ground, we can't fall any further. So that is why this goes to 0, because our height at position B is 0. Now, our kinetic energy at A is also going to be 0. And that's because the formula for kinetic energy is 1/2 mva squared. And our speed is 0. So that means that whole thing is 0. So since VA equals 0 meters per second, then that means that our kinetic energy at this position is also going to be 0. All right, so what this tells us then, and this is assuming that there are no losses. Now this is, again, a lie. There's absolutely going to be a loss because there's friction, air resistance, for example. So it will not actually hit at the speed. If there was no atmosphere, it would. But since there is an atmosphere, this is an exaggerated amount. So the kinetic energy is equal to 1/2 mvb squared. Our gravitational potential energy is equal to the mass times g times h. the height at position A. Well, if you notice something, the masses cancel out. So it doesn't matter what the mass is, the speed will be the same. So whether it's a 5 kilogram object or a 50 kilogram object, it makes no difference. Now, of course, that is excluding air resistance. Next, we need to get VB by itself. So I'm going to multiply both sides by 2. So this gives me VB, VB squared is equal to 2GHA, or VB is equal to the square root of 2GHA. So that's 2 times 9.8 times the height, 100 meters. That is 44.27 meters per second, or 159 kilometers per hour. So that would be quite an impact, to say the least. Now, of course, in real life, it would be less because friction will steal some of that energy away in the sound of heat, in the forms of sound, heat, and possibly vibration, but that's what sound is. So mostly heat and sound. And finally, the last little bit we're going to talk about is the concept of power. So power is defined by work over time, all right? And its units are in watts. So power is measured in watts, work is in joules, and the time is measured in seconds. So this explains why that you can do the same job, but the faster you do it, that means the more powerful you are. So for example, running up a set of stairs. The faster you run up the stairs, now technically you're doing the same amount of work. You're lifting your body from the ground to the second floor. So whether you do that quickly or slowly, the amount of work that you do is the same. But the faster you do it, the more power is required to do that job. This is why, a Lamborghini versus a 1982 Toyota Corolla, both of those vehicles can accelerate up to 100 kilometers per hour. Just the Lamborghini can do it much, much, much faster, or in less time than the Corolla can. So both can do the same amount of work technically, just the one vehicle is significantly more powerful. So let's take a look at this example. How much power is required to lift a 10 kilogram mass 2 meters if it takes 1 second versus half a second? All right, so in this case, since we're lifting 10 kilograms, we're doing gravitational potential energy. So the work that we're doing is going to be mg delta h, which is 10 times 9.8 times 2, divided by our time, which is 1. That's 196 watts. But if we do the same thing, but in half the time, that works out to 392 watts. Same job, half the time, double the power. Now, here's a key thing. In the automotive industry, we often refer to power in terms of horsepower, 1 HP, which is approximately equal to 746 watts. Now, where did this term horsepower come from? Well, it actually came back in the early days of electrification. Back before electricity was widely available for industry, both industrial and agriculture, beasts of burdens, such as horses, specifically work horses, were required to do certain jobs. So once electricity became widespread through urban and rural areas, the ability to market these new electric motors had to communicate how many horses it could replace. So a single horsepower motor could replace a job that would normally take one workhorse. A 2 horsepower motor would replace 2 workhorses, so on and so forth. And that's why the term horsepower was used. Now, it just stuck, and then when we refer to the power of vehicles, we still use horsepower. So if you have an engine that produces a modest 130 horsepower as far as cars go, that would actually be 130 horses required to produce the same amount of power your car can produce. So if you can imagine those monster supercars that produce 700 horsepower, that'd be quite the chariot back in the day. So the other power formulas, power versus speed. So power is also equal to the net force acting on a vehicle times its speed. Now this formula applies for constant motion. So let's say you're driving your car at a constant speed on the highway. The amount of power is being used is based on how much effort your engine is producing versus times your speed. Now, in this case, the reason why we're not accelerating is because the force of friction is equally balanced out with our force of our engine. So the power that your car is consuming is equal to how hard your engine is pushing times the speed that you're going. Now, if the car is actually increasing in speed, we use a slightly different formula, and that is force is equal to V1 plus V2 divided by 2, or F times your average speed. This is assuming that we're accelerating at a constant rate. So power is equal to F times V for constant, or power is equal to F times V1 plus V2 over 2 if we are accelerating. So let's do an example. How much power is required to lift a 10 kilogram object at a constant velocity of 2 meters per second upwards? All right, so the power is equal to the force times the speed. Well, the thing is, if we're lifting an object, that is our lift force. Well, what is our lift force? Well, assuming that we're going at a constant motion, our lift force must be equal but opposite to our force of gravity. So our FL is equal to our FG, skipping a whole bunch of steps, of course. So FL is equal to mg, so this becomes mg times V. So that's going to be 10 times 9.8 times 2, and that works out to 196 watts.